This is the geodesic dome for ASM International. This facility was completed in 1959. It was built on farmland donated by our secretary of the society, William Hunt Eisenman. They had a vision that was realized by this facility back in the late 50s, and it still reads as a very modern building today. This is a geodesic dome made out of aluminum alloy. It's 11 miles of aluminum alloy extrusions. It's a concept by Buckminster Fuller, who came up with the concept of a geodesic dome, and this particular one was designed by T.C. Howard. The structure goes as deep as 70 feet into the ground to support the dome. The dome is a very efficient engineering structure. If you want to cover a very large area with a very minimum amount of material, the shape is a sphere. That's the minimum amount of surface area to cover an area. And to have a sphere with these 56,000 different pieces, you see the structure itself is repeating hexagonal patterns. For materials engineers like myself and many of our members, structure is represented by these types of models. So not only is this an efficient engineering structure, but it's a great symbol for our society in that it also models how we're working with the structure of materials and how that affects the properties and how you can manipulate the structure to get the properties that you want. ASM was American Society of Metals back in the mid-50s. That's what the ASM originally stood for. So within the garden here, there are 66 different minerals that are important for manufacture of metal materials. This is two types of different iron oxide. It's an ore that you would use for making iron and steels. This fountain was created in 2000. Eric Orr's last monument that he made, or last sculpture that he made, is called ASM Singularity. And represented in this fountain are a stainless steel around the different layers of the fountain. There's another fountain in the back of the grounds. It was a tribute to William Hunt Eisenman, and his favorite saying was, "Make no small plans." So when they made the plans and decided to make ASM headquarters out here, they weren't making small plans, and that today it still looks like a very modern and interesting facility. Still captures the imagination of the people. This is our lobby to the building. Back when this building was designed, the open field was in vogue. There's a couple features in this room I'd like to point out that was original, is that you see these lights along the ceiling. You can see how it reflects into the dome space and around the circle of the structure. So you'll also see some of these panels throughout. These panels were commissioned in 1953, and they're by an artist called Nikos Beljan. He's got an interesting technique where he's done abrasion on aluminum panels, and the series is called The History of Iron. They tried to feature metals in interesting ways. So this hanging stainless steel staircase, the brass handrails, that was intentional examples of innovative use of metals. So this is our education lobby, and this wall of panels, and based on the size of those panels, it represents the contribution that was made. So there's a lot. We're fortunate to have some interesting companies that are supporting labs and testing and material science. Appreciate our education program here at ASM. So we're going to go into a heat treat lab where solar manufacturing has donated a vacuum furnace. We'll go into a microscopy lab where Zeiss has enabled us to have several research grade microscopes and an electron microscope. Buehler and Instron are our sister companies, and Instron is heavily invested in providing equipment for the mechanical testing lab, and Buehler manufactures and represents some hardness testing that's in the mechanical testing lab, and Buehler manufactures a lot of equipment that is for metallographic preparation. So this is a teaching lab for metallography. We have Allied High Tech polisher grinders, Buehler polisher grinders, Lico polisher grinders as some of their main features. And we have some mounting presses and some vibratory polishers in this room. In this corner, 3 or 4 pieces of analytical equipment for chemical analysis. The reason it's here is that my fume hoods are here, and these things generate some fumes that you have to get out of the buildings. Chemical analysis is the way you test to show that you have created the proper alloy chemically. So that was an ON8 measuring oxygen, nitrogen, and hydrogen levels. This unit over here is another LICO designed and set up to measure carbon and sulfur. that you need to know very accurately, and you need special equipment to do it. So this is a mass spec by mass properties, and often you would be dissolving alloys in an acid, and some of the acids are very nasty, hydrofluoric acid and things like that, and then you would sort them based on how much of different weights of different ions. That's the basics of mass spec. And metallography is a preparation technique so that we can reveal the structure of the materials. So in this lab, you have to go through a very gentle preparation technique where you section it to get the size that you need, the actual area you want to examine, and then you have to slowly remove material with progressively finer grits of media. So you do some fixed grinding initially with silicon carbide or diamond, and you would go down to finer and finer grit sizes. Then finally you polish, and you want to have a real flat surface with low damage, and then you would etch it chemically in the fume hoods to reveal the structure that's there. So it's called the microstructure. We come into our microscopy lab, and this is a teaching lab. It's kind of nice that we have our students right in the middle of the equipment that we would be using to analyze their samples. So the purpose of that microscopy lab is to provide a flat, damage-free surface that has the right contrast to capture the structure in this lab. So we're surrounded by some microscopes that are good at doing it. This over here is a electron microscope. It's a nice extra capability because all of these light microscopes, around 1000x is the highest magnification you can get. And you have to have a very well prepared flat sample. But if you need to look at a rough sample like a fracture or a failure, then you need something that has more of a depth of field. Depth of field being everything that's in focus at different heights at the same time. And if you use electrons instead of light, that's one way to get some very detailed images of those rougher surfaces. On the edge of the electron microscope is an EDS detector. And when you're impacting a sample with electrons, X-rays are given off as the electrons get bounced out of their orbitals. And so if each element has a characteristic signature of those X-rays that are given off due to the interaction of the electron beam with the material. If you can detect those and plot them, then you can do chemical analysis in a scope, and you can have some very nice capability. So we limit our class size to about 9 students in here, so that they were able to actually get a lot of hands-on time. And we designed most of our lab classes 50% lecture and 50% hands-on time. So you actually get in and use a lot of different equipment if you take one of our courses here. This is a microscope. This is a microscope that next year will be 100 years old. This was donated by the Milwaukee Electric Company, and it was about 50 years ago that this piece of equipment, and we kind of rediscovered the pieces and got them back together during our renovations. And it's kind of interesting that the optics hasn't changed. All of those microscopes in there have these same features of a light source. Their light source isn't a carbon rod and an open arc the way this one is. And it has using glass, using objectives and eyepieces to image, and then cameras is all still happening today in a much more sophisticated manner. This is a mechanical testing lab. In here we basically apply loads or forces to materials and then monitor their behavior. So this is a tensile tester where we're either going to be stretching metals or compressing and mashing metals. And most of the time we're stretching them. It's set up now with certain grips here. So this is set up to pull apart flats samples. So we want to really understand what's happening in the sample. So there's often a gauge length or a reduced section of the sample, and then we're going to pull this apart at a controlled rate of loading. So this is a test frame, a crosshead. This is a load cell to measure the loads that you achieve during the pulling. And this is a video extensometer, which is one nice non-contact way to measure the stretching. So you can see here we kind of painted some dots on here. This camera and the LED lighting lets you identify those dots and then measure while they're pulling apart. So design engineers and all of us need to know when things are going to break and when things are going to bend. How far can you pull it before it breaks? This is an electropulse. It's a cyclic loading machine. It's got an electrolinear motor up here, so you're able to change the shape of the loading. You can have triangular loading, sine loading. You can model loading that you measure from a car or an airplane and model it here, type of thing. So this can vibrate or load axially up to hundreds of hertz, but it also can do torsional. So this load cell here can measure torsional and axial loading. You can do some testing. We can give you fatigue life, and you can do fracture mechanics testing on here. So this is expensive. If I wanted to pay someone to machine this and give me results from it, it's probably $80 to $100 for each one of these samples. There was a real need to come up with a test that lets you know things are all right, they're heat treated properly, and that test was hardness testing, where you put a dent and either measure how deep the dent is, or you're measuring the size of the indentation with a controlled indenter and controlled loading conditions. So like this is a Rockwell test. It has a diamond cone as the indenter. This is a test block where you would have a known value, so that if I test that test block the right way and the machine's working, I would get the hardnesses of that test block. So it's this Rockwell test is a very sensitive test for measuring distance. And then we go to micro hardness testing, and that's what this is. We have ability to have a sample, and it turns out that the sample is a lot like those metallographic samples. It's got to be very flat, and it has to have really good contrast. An as polished sample works very well with micro hardness testing, especially now that things are automated. And this is a micro hardness tester that is very manual. You measure in the eyepiece the shape of the dimensions, and normally 1 or 2 diagonals, and then you bring it down, and then you have to dwell for 10 seconds or so. So every indentation takes about 20 to 30 seconds. So now that you have automation of a fully motorized stage, a camera that measures the indentation, and a stage that can lay down predefined patterns, you can do hundreds of indentations. So this is our heat treat lab. Before 2013, we basically had some box furnaces to do different temperatures. These can do up to 1100 degree temperatures. This is a Taco induction hardener, and if you put a sample in here and you reverse the current back and forth rapidly, you can generate some heat on the surface of the part. We had some pretty basic heat treat capabilities until 2013, when Solar Atmospheres. So they designed and donated this vacuum furnace in honor of the 100th anniversary. It's got some nice capabilities, and now we have atmosphere capability. All of these heat treatments, if you just have them in an uncontrolled atmosphere, the materials can interact with the gases in the atmosphere, the oxygen in particular. But if you can control it with partial pressure of argon or nitrogen, or high vacuum, you don't have any of those oxygen molecules to interact and cause decarbonization or oxidation of the surface. So having a nice controlled atmosphere and very tight controls of ramps and holds really enables you to do some different things with heat treatment. We have it hooked up to a liquid tank of argon. We're applying about 100 psi to control the valves. It's a backfill. And then when we quench or cool down from that after that hold, we're going to get the argon in there as quick as we can. And on the back there's a fan that's going to be rotating the argon through the furnace and through a heat exchanger to do the cooling. So let me show you, this is a really old hardness tester. So you saw the hardness testers in the other room. Those are maybe 10 years old. This one's probably 50 or 60 years old. So, and this one you don't have to plug in. You just do the hardness test and you read it right off the dial. This is a Rockwell hardness tester. So when we're manipulating these thermal histories, we're trying to establish a certain range of hardness or certain mechanical properties. But what we're really doing is changing the structure in a way, and our metallography lab is the way we would reveal that structure. So the labs are all kind of real basic materials processing, but they all work together to get the materials to the property levels that you want. In addition to adding the chemical analysis that we've done this year, We've added a computed tomography lab and a powder characterization lab. Parker had a big part of that. Nikon has partially donated, and Parker has partially funded this computed tomography unit that we'll see in the next lab. And it's almost $1 million unit. So it's the capability of our corporate partnerships and manufacturing partnerships and their appreciation of working with ASM has enabled some real nice capabilities. So this next lab is the computed tomography lab. Additive manufacturing is kind of an exploding technology, but we've been very careful and very fortunate to add capabilities that also accentuate our main programming. So this is a CT scanner. CT stands for computed tomography. And we have a source for X-rays. And this source for X-rays has a little filament like that. So it has leads, and you run a current through this filament and gives off electrons. Then you accelerate those electrons to hit a target. There's a tungsten target right here. When it hits the target, it's knocking electrons out of the atoms. The atoms fall back in and give off X-rays. That panel in the back is a detector. 2,000 by 2,000 different pixels. They're 0.2 millimeter round pixels that detect the energy of the X-rays. So we're able to use the CT scanner, has the resolution to look at powders and the penetrating capability to look at some parts. You capture the images over here, but you need a lot of horsepower to create these volumes and query them. And that's what this is, a reconstruction computer. So taking the data from a CT scanner and creating it something useful. This is a Snickers bar, a CT of a Snickers bar. And when you do the reconstruction of the volume, I can see much more detail than in one image of the X-ray. This is a confocal microscope, and it's using laser, cycling laser, to get very accurate height measurements. I do kind of feature this a little bit. It's almost part of the building tour, but this is one of those 5 supports for the dome. And it comes down into a little garden area with a fountain here. So we're actually underneath the grass roof, and if you have windows over here and this courtyard here, it doesn't feel like you're in a ground floor or a lower level. So this is the powder characterization lab. It's basically a clean room, but it's a clean room with the pressure set up so that we're not wanting the powder to contaminate the rest of the building. This is not really an industrial shop where we're doing manufacturing, and the powders are small enough and have enough potential health effects that we want to control that and keep everyone safe. So this is basically an airlock. So we would go in and gown and put on our respirators to go actually do the testing. So the properties of powder changes with the humidity and temperature. So this is a controlled temperature and humidity environment. We're in here, we have a couple of HEPA fume hoods. The entire room is filtered, and the air is rotated and filtered 20 times an hour. Cam Sizer X2, you stream a powder dry past a couple of high-speed cameras, and you're able to measure the shape and size distribution of millions of powder particles. Inside the fume hood, because it's a little bit dirtier application, is a rheometer. So the way powder behaves under load or with air blowing through it or at different speeds of movement are all things you would like to measure and understand if you're trying to feed powder or control the flow of powder in a machine.